All right, let's get into our magnetism review. The first thing we talked about in this unit was the magnetic force on a moving particle. And with this, obviously, if your charged particle Q is not moving, you do not have a magnetic force. That X in the middle is for the cross product, so forgive the poorly drawn hand, but if that's your thumb, and that's your pointer finger, and that's your middle finger, these are your knuckles, if you hold it out like a gun with your middle finger pointing out towards the palm of your hand, that tells you, and your thumb pointing straight up, that tells you the direction of the force given the velocity and the magnetic field. Well, and that implies something a little bit different about the magnitude. So you do the cross product for the direction. For the magnitude, the force is QV times the magnetic field, B, times the sine of the angle in between the velocity and the magnetic field. And what this means is that when they're 90 degrees to each other, we have the biggest force, and when they're parallel, we have zero force. And so a lot of the things that we do with this, let's say we have the magnetic field coming into the page, as shown like this. To save some time, we're just gonna do a little bit. And if we have a positive particle, I want that to be blue. If we have a positive particle and it's moving with a velocity in this direction, hold out your gun. Put your pointer finger in the direction of your velocity, so point that to the right. Put your middle finger down into the page, and your thumb is up. So what that tells you is that the magnetic force acting on this particle is up. And so with these things being at 90 degrees to each other, it's going to loop around in a circle. So you get a circle, a charged particle trapped in a circle. Only when the velocity is at 90 degrees to the magnetic field. And in the case when you're going in a circle, the magnetic force acts as the centripetal force. So we'll say is centripetal. So that means that the acceleration can be written as centripetal acceleration v squared over r, and the magnetic force does no work. Because it's going in a circle, let's draw our circle, the velocity is tangential to the circle at all points. The radius points that way. Sorry, that is not correct. The velocity is tangential. The force points in. So if your velocity is that way and your force is that way, your displacement is at 90 degrees to your force, and it does no work. Also, that magnetic force is not going to speed that up or slow that down at all. When your velocity is not at a right angle to your magnetic field, but it's not parallel, you get a helical shape. That's the spiral. Okay, so let's say your magnetic field, points in that direction, and let's put the velocity of our object like this. You have a component of your velocity that is parallel to the field, so that does not change. So it's going to continue moving with the magnetic field. And then you have a perpendicular component. That perpendicular component is going to spiral around, and so you're going to get a helix like this, where the velocity is in the direction of the magnetic field because of that part that does not change, but you're spiraling around that magnetic field. The types of problems that we see with this, this is the mass spectrometer kind of problem. So in a mass spectrometer, what you have is the accelerating region. You've got two plates, a battery, and a hole. So you have a potential difference here. You're going to put a little tiny positive charge there. It's going to accelerate through the hole and go into the region of a magnetic field. Let's pretend the magnetic field B is out of the page. Oh, actually there are two different regions. So it's going to move into this magnetic field region. So region 1 is our accelerating region. Region 2 is our velocity selector. In region 2, we have an electric field and a magnetic field. And then in region 3, we'll say E field, we have our magnetic field. So our particle is accelerated through here. It'll experience a magnetic force and an electric force that are arranged such that it goes straight through that region, and then it hits the mass spectrometer. So if we have a positive particle moving that way with the magnetic field out of the page, it's going to go in a half circle that's pointed down. Okay, so we'll look at what happens in all three of our regions. In region 1, we have an accelerating voltage. So in region 1, the thing's going to have potential energy on the left-hand plate. It's going to equal to the kinetic energy it has once it leaves that region. The potential is given by the charge times the EMF of the battery. That's what the plates are charged to. And that's going to equal the kinetic energy at the end, 1/2 mv squared. That's one way to find that velocity. In the second region with the velocity selector, that's what we call that. For our positive particle, we saw that the magnetic field had to be down. So we're going to have an electric force that's up. So we say we have an electric force that's up, and since it's a positive particle, that also means the electric field is going to be up. And we say that the electric force, Q times the electric field, is equal to the magnetic force, QVB, and then we can find that velocity, or we can find the magnitude of the electric field. And then in region 3, that's where we have our net force is just equal to the magnetic force. So our net force is, since it's moving in a circle, mv squared over r is equal to qvb. So we can figure out the radius of that circle, or the radius of the circle can give us the velocity of the object. Or if we know the velocity from the velocity selector, it can tell us the amount of charge and the mass of the object. Anything you need out of that. So that's the basic mass spectrometer problem. While we're talking about forces, although we're not going to spend a lot of time on that yet, is we have the force on a wire. Force on a wire in the magnetic field. So with that, we have the same idea with our cross product. The force on the wire is equal to the current times the length of the wire crossed with the magnetic field. And again, for our poorly drawn hand, our thumb goes with the force, our pointer finger goes with the length, our middle finger goes with the current. And then those are your leftover fingers. Hold your right hand out like a gun. That's for direction. For the magnitude, force is equal to ILB. And again, we have that nice, let me erase that. Our force is equal to the current times the length of the wire in the magnetic field times the magnetic field times the sine of the angle between the length and the magnetic field. We're not going to do any calculations with that yet. That's just one way to do it. After we talk about Ampere's law, we'll talk about that. As far as sources of the magnetic field go, well, that's next. So for this next bit, what we're going to say is creating magnetic fields. And the big idea here is that moving charges create magnetic fields. So we have a French guy, two French guys, Biot and Savart. So our Biot-Savart law says that the magnetic field created by a single moving charge is mu zero. It's the permittivity of free space divided by 4 pi times that charge times that velocity divided by however far away our point is squared gives you the magnitude of the field. To get the direction, and this is how I prefer to write it, the direction of the magnetic field is equal to QV, because if you have a negative charge it's going to change, crossed with how far away from that moving charge that you are. Those things being your vectors. And again, because it's our right hand rule, our thumb goes with B, our pointer finger goes with V, and our middle finger, which looks incredibly strange. Nope, that's the wrong one. Our middle finger is going to go with R. And that's how your right hand rule would work for that. Looks like you have a problem that needs to be taken care of. So, if we have a positive charge that is moving in this direction, the magnetic field created by that positive charge, at this spot here, the radius points to that spot. So take your pointer finger, point it in the direction of the velocity. Point your pointer finger in the direction of velocity, your middle finger up towards the radius, and you'll see your thumb coming up at you. So you'll have a magnetic field out of the page, and in fact your magnetic field is going to come out of the page and sort of swirl around the direction of the velocity. And the magnetic field, since it's over r squared, is going to get weaker the further and further away you move from that. So that's how you find the magnetic field from a single moving charge. And this is where we get permanent magnets. Permanent magnets come from electron spin in atoms. When they line up, you have a magnetic material. So iron has the ability for their electron spins to line up. Permanent magnets have them frozen in place. Regular material just has random directions for the spin of electrons, and so they all cancel out. The next thing for the Biot-Savart law is the more difficult part. It's from a wire. The differential piece of the magnetic field from a wire is equal to, again, mu 0 over 4 pi. This is kind of like K for the electric field. It's just a constant that we multiply things by in order to get the numbers to work out right. So mu 0 over 4 pi equals the current times the differential piece of length of the wire divided by r squared. That's to get the magnitude. In order to get the direction, and I'm not going to draw the hand this time, but the magnetic field, as far as the direction goes, the direction of the magnetic field is IDL cross R. So, the cases that we had to use that for, well, we'll just talk about the basic setup with a line of current that's moving this way. You have a tiny piece of DL here, and you have your point that's a distance of r is not the best thing to use. We'll say it's a distance of x away, and dl is y down from where we're going to start. So if you point your finger in the direction of the current, rotate your middle finger out to point at that point, you'll see that at that spot the differential magnetic field is out of the page. And so dl would be dy, and your radius would have to be that weird x squared plus y squared thing. Now it gets really strange because the radius has an angle, and so we're not actually going to calculate this. We're going to use something else that's more convenient. What we do have to do is a ring of current. And so for a ring of current, and we'll see how well drawing this goes, you have a ring of current. Some of it, so that front end comes out of the page, and this back side goes into the page, and then our axis is going to extend. Well, let me do another color so we can see it better. Our axis is going to extend like that. We'll say this thing has a radius of a, and we'll say that our point is a distance of x away. So if this bottom piece is my dl, and my current goes that way to where my current is into the page at the bottom, and my current is into the page at the bottom and out of the page at the top. That's going to let us talk about the magnetic field at this point. So if dl is into the page at the bottom, and my radius points to here, the first thing as we set this up, well, look at it. So dl is into the page, my radius points that way. So from that bottom piece, my differential magnetic field points that way, which is at 90 degrees to my radius. So what we have is dB is equal to mu 0 over 4 pi times I dl over r squared times the sine of the angle in between dl and r. Now if we look at what we just did, theta is 90 degrees, so the sine of that comes out to be 1, and we don't need it anymore. But, so that takes care of that sine theta part. We no longer need to pay attention to that. But because of symmetry, if we look at a similar point on the top, we have a similar magnetic field that points this way. We only need the x component, dB in the x, of our magnetic field. And for that, we have to look at this angle. And for convenience sake, we're going to call it phi, just because it's a different angle. So if that's phi, then that is phi as well. And so the x component of my differential magnetic field, dB in the x, is equal to, and again, mu 0 over 4 pi times I dl over r squared. And now we have the sine of this angle phi, just because of symmetry considerations. This is something different than the magnitude that we get from the cross product. This is something that we have to deal with because of symmetry arguments. Now we're all ready to go. So when we take, well, we're not quite ready to go. Sorry. So from this we see that r is equal to x squared plus a squared, and we see that the sine of our angle is equal to sine of our angle phi is equal to a over x squared plus a squared square rooted. So we're going to have to put all of that in here, but when we take our integral, our magnetic field comes out to be, well, mu 0 is a constant, 4 pi is a constant. As far as our integral is concerned, we have constant current all the way through, We're going to divide that by r squared, which is, a squared plus b squared. Sine theta does not change as we go along, so that gives me a over the square root of a squared plus b squared. So this little term gets to go to the 3/2, which is familiar to us. And then we have to deal with dl, because that's the only thing that's going to change in our integration. And that's going to tell me the length of the wire that has current running through it. So for what we have, dl is 2 pi a. This would be the magnetic field that we get from this. And the direction of the total magnetic field would point away from the axis for this particular ring of current. Not x squared plus b squared, a squared plus x squared. Sorry about that. So that's one case that we have to do the Biot-Savart law for. The other case is, and we'll do it up here, the arc of charge. Sorry, arc of current. So for the arc of current, we have current running down. We have a semicircle of current, and our current continues to run down. And we're going to look at the magnetic field at this point. So, in this, let's say, that's my piece of dl. My current's running that way. So dl runs that way. R is in that direction. And at every point, dl is perpendicular to r, so that's good news. Also, doing our right-hand rule, if we point our finger down and our middle finger towards the center of that circle, we see that the magnetic field is coming up at you, the differential magnetic field is coming up at you. So for our arc of charge, dB again is mu 0 over 4 pi times I dl over r squared times the sine of the angle in between dl and r. And when we do that, again, that angle is always going to be 90 degrees. And here there are no symmetry considerations. So we're ready to go ahead and take our integral. That tells me that b, the integral of db, is equal to mu 0 over 4 pi, those things are constants, times I, that's constant for the entire thing, divided by r squared, that's constant for the entire thing, and then we just have to deal with dl. In this case we have a semicircle, so dl is just pi r. The joys of algebra where things cross out. Pi's go away, one of my r's go away. The magnetic field at the center there is mu 0 I. Sorry for the phone, that gives me mu 0 I over 4 pi r. Okay, so these are the things that we're going to have to do the Biot-Savart law for. The Biot-Savart law is not great. But these are simple cases. It doesn't do any integration that's beyond our pay grade, so that's nice. The last thing that we have for the magnetic field is Ampere's law. Again, it's another French guy. I don't know what's up with them in magnetism. We'll reclaim this soon. So, Ampere's law. Because it gives us a convenient way to find the magnetic field from a current-carrying wire. So, say we have a very long current-carrying wire. If we attempted to do Gauss's law, so current carrying wire, we have a magnetic field. Let's say my current is this way. We have a magnetic field that spirals around this current carrying wire in little concentric circles, getting weaker as it goes out. If we were to, and we'll put a note of this over here, if we try to do Gauss for the magnetic field, Gauss's law for the magnetic field does not yield a great result. So if we take the closed integral of the magnetic flux B dot dA through a surface, what we notice is that there is always going to be zero flux. The magnetic flux through any closed surface is zero because of that looping thing. One of the implications of this is that we cannot have a magnetic monopole. No matter how much you split up the magnetic field, no matter how much you split up a magnet, even down to the atomic level, you will always have a north and a south end of a magnet. So, that gives us Ampere's law. Ampere's law is a line integral. So if we take this same bit of current, and we look at it here, current running into the page, we have a magnetic field that goes sort of this way around it. What we're going to do is a line integral. We're going to take a line and we're going to start here and we're going to integrate all the way around that line with the magnetic field. And what Ampere's law says is the product of the line integral, the closed line integral of the magnetic field times the differential piece of length of that line is going to be our fundamental constant mu 0 times the current enclosed by that, what we call, write it down here, Amperian loop. Amperian loop. It's a fake loop. We're making it up. Now, we're going to pick situations that are convenient for us. So because of the symmetry of this wire, B is constant, so it comes out. We just have B times the length of this loop. In this case, it's 2 pi r, and that's equal to mu 0 times the current in that wire, because it's enclosed by our Amperian loop. And so what we get is the magnetic field from a very long wire is mu 0 I over 2 pi r. So that tells me is the magnetic field gets weaker and weaker and weaker as we move away from our wire. Now, this will always be true outside of our wire. What's going to be fun is going inside of our wire. And so, to save time, we're just going to look at the cross-section of the wire with bits of current going into the page inside of the wire. And so what we're going to do is put our Amperian loop here. We're going to say our wire has a radius of big R, our Amperian loop has a radius of little r, and what we want is the magnetic field inside of the wire, inside of that little bit of r. So, Ampere's law looks the same. B dot dl is equal to mu 0 times I enclosed, and so the B dot dl part is still B times 2 pi little r, but we have to deal with I enclosed. Now, I enclosed is going to be the current density, we call it J, times the enclosed area by our little bit of r. Well, J is the total current, that's I enclosed, the total current I divided by the total current by the total area times A enclosed. So that is the total current divided by pi big R squared times pi little r squared. Our pi's go away, and so my enclosed current is equal to I times little r squared over big R squared. So that's what goes in here. So when we do it, we got B times 2 pi little r is equal to mu 0 times I times little r squared over big R squared. One of my r's goes away. The magnetic field inside is mu 0 I times r over 2 pi times the radius of the wire itself squared. And so we see that the magnetic field increases as we go outside of the wire. Now with this, there's always the possibility of getting nested wires. what I mean by nested wires is that you have two conductors in a long cylinder, and one of them you have the current going into the page, and the other one you have the current coming out of the page, and we can get as complicated with that as we want. We just have to remember that if we draw our Amperian loop, the only thing that matters is the stuff inside of that Amperian loop, not on the outside. So all you have to do is calculate the enclosed current. Okay, so the next piece of this is the solenoid. And that's multiple wraps of wire with current running through it. So if we have current running in here, and we have multiple wraps of wire, solenoid running out. That's our solenoid. It's very long. To give us a cross section of the solenoid and a slightly better picture, it's a cutout, a cross section of it. And what we'll say for convenience sake is that on the top, current is into the page, and then on the bottom, of course, since we're talking about wraps and wraps and wraps of wire, the current is out of the page. So, in this case, for our Amperian loop, if we do a loop that encloses both the inside and the outside, we see from that part of the loop that the enclosed current is 0, telling me that the magnetic field outside of my solenoid is 0 because I'm enclosing 0 current. So that leaves us with putting an Amperian loop that only covers one part of this. Now, the way that we describe these things, a solenoid, we talk about in. It's the number of turns per unit length. That's going to become important when we talk about how much current we have. So, first off, for the solenoid, the magnetic field is out of the page here. Any point along here, the radius is up, and so in the middle we're going to have a magnetic field that points that way. So when we do our Amperian loop, we're going to integrate around from 1 to 2, 2 to 3, 3 to 4, and 4 back down to 1. So as we set up Ampere's law, we've got a closed B dot dl, and that's why we have to go all the way back around to 1, because the closed line integral is equal to mu 0 times my enclosed current. So this side we have mu 0, and my enclosed current, well, each one of these dots has current I running through it. So I have I times the number of wires that I am enclosing, which is N times the length here, L, of my Amperian loop. That's how much I'm enclosing. So the B dot dl side, our line integral side, looks a little bit different. We have 4 segments of line, so we're doing B dot dl for 4 different regions. From 1 to 2, plus the integral from 2 to 3, plus the integral from 3 to 4, and I'm sorry that I ran a room, plus the integral from 4 on back down to 1 of B dot dl. So if we look at the first one, from 1 to 2 we have 0 magnetic field, so that doesn't give me any contribution. From 2 to 3 we notice that our magnetic field is at right angles to our length, and so that dot product gives me nothing. Then from 3 to 4, let's do that in red so you can see it. From 3 to 4, the magnetic field is parallel to our length, so I have a contribution there. And then from 4 on back to 1, we are perpendicular again, so that goes away. So from 3 to 4, it's B times the length. Well, that's just B times L is equal to mu 0 times I times N times the number of turns divided by, just that, sorry. We have an L on both sides, so the magnetic field from the solenoid is mu 0 I times the number of turns per unit length in the solenoid. And notice that there's no dimensionality to that, so that tells me I have a constant magnetic field of this magnitude inside of the solenoid. The AP test may try to throw slightly more complicated situations at you, like the slab of infinite width. We did an example like that in class, but it's an application of Ampere's law. And what we really want for Ampere's law is our magnetic field to be parallel to the length that we're going to integrate over. Okay, so the last thing that we have is forces between wires, and then possibly magnetic flux. So, I feel like we're not really supposed to do forces between wires until we've talked about Ampere's law. So, let's call that I1, we'll call this I2. Now, from our right-hand rule, from I1, magnetic field 1 is into the page, and magnetic field 1 from Ampere's law is mu 0 I1 over 2 pi r, where r is the distance separating these things. Now that I have magnetic field 1, the force acting on wire 2 is I times the length of wire 2 times the magnetic field that it's in. And that's the current of wire 2 times the magnetic field that it's in, which is B1. So the force on wire 2 from wire 1 is the current 2 times the length times mu 0 I1 over 2 pi times the distance separating. That's how we get the magnitude of the force. To get the direction of the force, current is running to the left, the magnetic field is into the page, and so for wires running opposite to each other, that force pushes down and pushes up. It acts to separate them. And from Newton's third law, we know that the magnitude of each of those two forces has got to be the same. When two wires run in the same direction, current I1, I2, the magnetic field from the first wire on the second wire in this case is still going to be into the page, just because of the direction that we drew it, magnetic field 1. But in this case, since the current is going that way, the magnetic field's into the page, these two forces act to bring each other together, and you find the magnitude of that force the same way. The next thing that the College Board likes to do is give you one current this way, and then near that, a current carrying loop of wire like this with a different current in it. We'll say I2, and we'll say that I2 goes this way. And they want to know the net magnetic force on that loop of wire because of current 1. So if we look at the magnetic field from current 1, we do our right-hand rule, we see that the magnetic field is out of the page. That's what all these dots are supposed to be. So we have a magnetic field that is out of the page because of wire 1. We'll call it magnetic field 1. So, because of that, the magnetic field is out of the page, the current is over. We have a downward force on this part of the wire and an upward force on this part of the wire. And then magnetic field is out of the page, force to the left, force to the right. Now, these sidewave forces have the same magnitude, so they cross out. But that force is bigger because it's closer. right? The magnetic field is stronger at that point. Magnetic field at this point would be mu 0 I1 over 2 pi r. The magnetic field up here would be mu 0 I1 over 2 pi r plus a. So the net force on that thing would be the difference between those two forces. Again, where the force is the current I2 times the length of wire times that magnetic field that we just found from Ampere's law. And then the next thing that College Board likes to do is ask you the flux through that thing. Magnetic flux there is the integral of B dot dA. And since it's not a closed surface, it's just one loop, we can actually do that. So here we know the magnetic field is mu 0 I1 over 2 pi r, and dA is our differential piece of area. What we want for dA is strips that run in that direction, because the magnetic field is constant in the x direction, but not so much in the y direction. So mu 0 I1 over 2 pi r times, our x dimension L times dr. And we're doing that from the top, I'm going to say r, from the bottom to the top, r plus a. And so taking that integral, which is just r over dr, from r to r plus a, is going to give you the flux through that loop. This isn't terribly important for the unit we're in now, but for the next one it is going to be. That's it for our video.